So you and Maria are the session chairs. So let me see if Maria is around.
Yes, I'm already here.
Ah, okay. Yes. Oh, thanks. So then I'll also promote Maria as co-host. Okay, I don't see Maria. Okay, why you don't see her?
She's already a panelist.
Okay. Yes. Thanks. Yeah, I see. So you both are co-hosts now, and you can identify and promote the speakers. I think most of them, they become panelists. So I think, I guess everyone's here, except no, I think everyone's here, I suppose. Oh, Lorenzo and Marcus are authors of the third paper. I mean, one of them should give the third talk of the session. But can you see them by any chance? But anyway, if they join us attendees, in case, you will be able to promote them as panelists, and then they can turn on their video and audio.
Okay.
Can I share my screen already?
Yeah, sure.
Do you see my presentation?
Yes.
Okay.
So the second talk would be given by Pranab. Is that right? Yeah, I see.
Yes,
Pranab.
that's right. Yeah.
And fourth one would be
Iran, I guess.
Iran, all right.
The fifth one will be by Shahram.
Okay, all right.
So only Lorenzo and Marcus, they are not here yet. Okay, I think so. It's on time, I think. Yeah. So the session is yours.
Okay. By the way, could you help to post the Zulip chat link on?
Oh, yes. I know if you scroll the chat all the way up, you will find the link to the Zulip chat. So you can use that to sign in.
Maybe we should have the first speaker's screen. Right.
All right, guys, let's start. So thanks to everyone for attending this session of IndoCrypt 2020. Right, so for this session, we have 5 talks, and I'll be chairing this together with Maria. So our first talk is actually cryptanalysis of the permutation-based algorithm, SPOC, joint work by Lilia Kraleva, Raluca Posteoka, and Vincent Ryman. And it'll be presented by Lilia. Right, over to you.
Thank you for the introduction. I will talk about the algorithm SPOC, which is a second round candidate to the lightweight competition, which started in early 2019. In our work, we constructed characteristics for the SLI SCP light permutation, which is the permutation used in SPOC. Then we use this characteristic to perform tag forgery attacks on both SPOC versions. Furthermore, we present message recovery and key recovery attacks on SPOC 64, one based on the differential characteristics again, and the other working regardless of the permutation and the number of rounds. And finally, we also give some observations on the constants used in the permutation. So I will try to give the intuition about the tag forgery attack. In this figure, you can see how the encryption of one message block will look like with SPOC 128. First, you can see that the key and the nonce are loaded to the state, which is the entire initialization phase for SPOC 128. Then the messages are absorbed to the capacity part, and the ciphertext are produced from the rate part. After each block, a constant is added to the rate part of the state, and the value of this constant depends on the current state and the size of the message. Here we are encrypting a message with no associated data, and the entire associated data processing phase is completely skipped. Finally, another constant associated with the tag generation is added, and then the tag is produced. Now, if we take a second message, so the first message M is incomplete message, and the second message M star is complete message block, which is the padded M with some difference added to it. Now, the difference in the processing of these two messages is only the size of the added constant, because the first message is incomplete and the second is complete. So if we we searched for differential characteristic with an output difference in the rate part equal to delta 1, which is the sum of those two constants. If our characteristic holds, then the output difference in the capacity will be cancelled by the difference in the messages, while the difference in the rate part will be cancelled locally by the constants. Then the internal states after this will be the same, and therefore the produced tags would be equal. Our tag forgery attacks are based on this property, and you can see more details in the full presentation or in the paper. Both our message and key recovery attacks are on SPOC 64. In the figure, you can see how one message would and the encryption of one message block would look like in SPOC 64. And as you can see, the initialization phase is different. For SPOC 64, we have the loading of the key and half of the nonce to the state. Then a permutation is applied, and then the second half of the nonce is added to the capacity, to the capacity bits. For SPOC 64, the initialization phase is not bijective, meaning that there are multiple key-nonce pairs leading to the same internal state. And this happens because the size of the key and the nonce together is larger than the size of the state. In both our key and message recovery attacks, we aim for a collision initialization phase, and we propose two ways to have such a collision. The first way is with a differential characteristic, which we use for the message recovery attack. And the second one is a time memory trade-off approach, for which we use equivalent key-nonce classes, which lead to the same internal state. Then the same message will have the same ciphertext over different key-nonce pairs. So to conclude my short talk, this is a table with all our attacks and their complexities. And I want to point out that our attacks are theoretical and do not compromise the security of SPOC, and also that all scenarios are in the related key, related nonce scenario. And it seems that all our attacks have complexity more than 200 and 2 to the 100 complexity, but we don't violate the 2 to the 50 data requirement encrypting of data encrypted under the same key, because all our attacks do not need the same key for the different encryptions. And thank you for your attention. If you have any questions, you can ask them now or send them by email.
All right, thanks, Lilia. So have you gotten any response from the Spock designers on your result?
Yes, and they claim, well, they agree, and we also agree that the results are theoretical. So the security is not compromised.
All right.
And that's why I pointed the 2 to the 50 data, because apparently this is their main reasoning, that we use more data than they claim is secure.
Okay. So probably we move on to the next talk, Maria.
Okay, so the next talk is on RC4, namely it's called More Glimpses on the RC4 Internal State Array. This is a paper by Pranab Chakraborty and Shubhamoy Maitra, and the talk is given by Pranab.
I hope my screen is visible and
yes,
I'm audible.
Fine.
Thank you, Maya. So the topic is more glimpses of the RC4 internal state array, and it deals with the stream cipher RC4. And what we mean by glimpses, we will soon see, and we will quickly look at the contributions that we have made. At that high level, if we have to look at the inspiration for the work is basically to look at how the biases of such stream ciphers are also linked with the internal state array, and how the internal state array's state can get leaked through biases. So this is a study in that direction. So if we look at our results on this particular paper, there are 3 categories of results we have outlined. One is that on the Jenkins glimpse, and I will quickly explain that, we have done further investigations, and the original result is from way back 1996. And post that, results around glimpses were not many, and this this allowed us to investigate the glimpses further. Then we looked at the Flurer-Magru biases and how that can be looked at from the lens of glimpses. And thirdly, we looked at how Jenkins' original glimpses actually get modified wherever Flurer-Magru biases are occurring. At a very basic level, any stream cipher, if we look at, this is a fundamental picture where message bits are coming and the key stream bits are XORed to produce the ciphertext bits. And at the decrypting end, the same key streams are XORed once again to retrieve back the message. Now, in case of RC4, how do we generate the key stream, that is ZI? I will quickly show that and then move on to the results. So if we look at the RC4's structure, we have in RC4 an S array, which is an S box that's of the length of 256 bytes. And there's a secret key which can vary from 5 to 32 bytes, which is expanded to the full 256 bytes. And that is used to initialize the S box. And if we look at the picture, I will go to the pictorial description. This is how the S box looks like. And there are 2 indices. One is I, which is a sequential index, which increases one by one. That is, it starts with 0, then 1, 2, then goes to 255 and wraps it back to 0. J is a pseudorandom index which is created based on the current value of SI. And when we look at SI and SJ, and all additions are modulo n here, modulo 256, when that is added, that yields a new location. From that new location, the Z or the key stream byte is recovered. And it is one of the most simplest in terms of if we look at the design, but it yielded at one point of time one of the most popular ciphers. And what is that we are talking about when we say glimpse? Now, glimpse is basically an aspect which is that for any such stream ciphers, the property is by looking at the key stream Z, that is Z1, Z2, Z3, we should not be able to conclude anything about the S box, any of the locations, whatever is the byte value. However, way back in 1996, it was showed by Jenkins that is not the case. And the result that he showed is the following. So what is showed is, if we look at this theorem, it says that in the location of I in the round R, which is IR, if we look at the value of S, that is related to J minus Z with the probability nearly 2 by n, which is almost double of the random association, which is 1 by n. And similarly, there is a dual, which is S value of J. When we look at that is also nearly 2 by n, which is a double of 1 by n. Now, this particular glimpse results, if we look at, it involves in every result, in both the results, the J value. Now, the J value is actually unknown because from the outside, when somebody looks at the Z stream, J is not known because it's a pseudorandom index. Now, is there anything that is possible to know about glimpses, which is not requiring J? So a corollary that we found out is the following. We have proved in this paper that every round, if we look at the consecutive 2 rounds Z values, and we add those, and we use that as an index. Now, the probability that a Z value in the rth round is equal to that value is more than the random association 1 by n, although the value of difference is not that much. It is 1 by n square order. However, when there is a certain condition of IR is equal to ZR plus 1 minus 1, it becomes almost equal to 2 by n. Now, we'll not get into the proof at this point in time in the interest of time. We'll show different types of results. We also realized when we were doing this analysis that there is a correlation that we can get. This is a theorem that we found out, that when ZR and ZR plus 1, that is consecutive 2 values of key streams, both are equal to R plus 1, then the Jenkins results actually gets modified. It no longer remains 2 by n. As you can see, the first result is 3 by n, next one is 3 by n. If we look at R plus 1th round, then one result is 2 by n and the other result comes down to 1 by n. Similarly, there is a 5th result, which is a different glimpse that we found out, and we have ignored the order 1 by n square terms here. Now, this is the first set of results that we shared. The second category deals with the Fleurer-Magru biases. Now, what is Fleurer-Magru bias? Fleurer and Magru in 2000, they came up with the fact that in RC4 key streams, in certain places, if we look at side-by-side 2 values of Z, then there are certain values which are biased, and it is more than 1 by n square, which is the random association. Similarly, over a period of time, there were lag1 digraph biases also that were found out. What is lag1? Lag1 is, instead of consecutive 2 bytes, we take one interleaved, that is a byte at 0th position, then the byte in the second byte position instead of 1. So that's the lag1 digraph. There are also certain biases were discovered in later point of time. And what we have found out is that whenever that happens, now this is a table we have come up with this result, is that whenever any Flurer-Magru biases are happening, as you can see, there are 12 rows. The source of ZR, we can find out where is it biased. And you can see that in Rth round and R plus 1th round, both rounds, if we look at source of ZR for A, source of ZR plus 1 for B, there are biased bytes, and some of the places the biases are 3 by n, some of the places 2 by n. And in fact, in some of the rounds, there are multiple source, you can say, glimpses that are observed. So this is what we are saying, that a proliferation of glimpse, multiple glimpse results that we could find from this. This is one category of results. We have proved the generic approach of proving how this is happening in the paper that can be found out. We have also showed that in lag1 digraph biases, the same thing is happening. And as you can see, some of the places, the biases are as high as 4 by n. The third category of results, let me go there, where we have showed that wherever Flurer-Magru biases are happening, if we look at original Jenkins correlation, which said that SI and SJ would be almost 2 by n, that completely gets changed, and that gets modified, and in many places it becomes 3 by n, in some places it is 4 by n, in some places it also comes down to 1 by n. And if we look at the lag1 digraph biases, there also that kind of changes happen. If we have to just point out some interesting result, one more I would like to highlight is that in this particular table, in the 12th row, if you look at, there is a particular probability of SR plus 1, IR plus 1 equal to 0. That is, if ZZ plus 1 value becomes 0, I plus 1, in that particular state, in the R plus 1th round, the value of S of I to be equal to I plus 1 is 0. So these are very strong probability values that that were found out. So to conclude, what we can say is that if we look at all these results, we find that there is a strong relationship between the biases and the glimpses. And since the S boxes are used in many other ciphers, the combinatorial study and analysis of this kind of relationship may lead to insights in other places, as well as cryptanalytic attacks, improved cryptanalytic attacks. So thank you. Thank you, everyone.
Thanks. Maybe a quick question, because we're already quite far on the time. So you mentioned further cryptanalytic results. Have you had a look how efficient your biases can be detected or exploited?
So that is the next set of results that we are exploring. We don't have a definitive answer to that, but we are actually working towards that direction.
Okay, interesting. And have you been able to practically verify the biases?
Yes, all these biases have been experimentally verified by running programs to the degree of satisfaction that we require. We have done that for all the biases. We have run the programs.
And you could confirm exactly the numbers that you predicted?
Yes, absolutely.
Mm-hmm. Okay, thanks a lot. I think we can now head on to the next talk.
All right. So our third talk for this session is actually by Lorenzo Grassi and Marcus Schaffnegger. Right, it's on mixture integral attacks on reduced round AES with a known or secret S box. So Lorenzo will be presenting.
Thanks for the introduction. You see my screen?
Yes.
Okay, perfect. So I'm going to present a few attacks and distinguish here on round reduced AES. And these attacks are in the low data scenario. So first of all, I would like to briefly recall what the low data scenario is. So in general, in cryptanalysis, we try to maximize the number of rounds that we are able to break without exhausting the full code book or the key tools. And this is important because, for example, this allows us to determine the security margin of a cipher, which means the ratio between the number of rounds that we are able to break and the number of rounds of the cipher. However, in general, these attacks are not practical. So another possible scenario that we can consider is the low data scenario, which is much closer to real life scenarios. So in this case, the time complexity is not limited. So, I mean, apart from the natural bound of the brute force attack, but we have a restriction on the data complexity of the attack. So this means that the attacker can only use few known or chosen plaintext for ciphertext. So the main contribution of our paper is a new secret key distinguisher for a free round of AES, which we call impossible mixture integral distinguisher. And as you can see, it's the one that requires the lowest data in the literature. So we have other distinguisher in the literature, like the truncated differential integral attack or yo-yo distinguisher. Yo-yo, okay, it's the lowest one, but it also requires adaptive chosen ciphertext. In the case in which we consider only distinguisher that requires chosen plaintext or chosen ciphertext, our distinguisher is the one with the lowest data. For example, for comparison, if you have a probability of success of 65%, our distinguisher just requires 6 chosen plaintexts, while a truncated differential distinguisher needs 12 chosen plaintexts. In a similar way, for a probability of success of 95%, our distinguisher only needs 10 chosen plaintexts and truncated differential about 20 chosen plaintexts. So this distinguisher exploits a zero-sum property, which is found using the mixture differential distinguisher proposed at FSC 2 years ago. And it is impossible in the sense that this property that we are going to use has probability 0 for the case of AES. Now, using this distinguisher, we are also able to present nuclear recovery attack on AES. For example, nuclear recovery attack on 4 rounds of AES, which requires 6 chosen plaintexts, and they don't use the details of the key schedule. And this is quite a trivial attack in the sense that it uses the same technique proposed for a classical zero-sum attack. And in a similar way, we can also consider the case of AES with a secret hash box. So in this case, we have 2 scenarios. In the first one, the attacker first finds the secret hash box and then uses this information to find the key. In the second one, the attacker directly finds the hash box using, directly find the key using a property of the mixed layer. And as you can see, our attack uses the first strategy, and it is the most efficient one in the literature. So I just would like to briefly present our distinguisher, which I think is the most important, is most interesting result of our paper. So in order to do this, I introduce this notation. So we are going to use plaintext of this form. So we have one active column, and the other columns are constant, and we are interested in the variables in the first column. So I denote this plaintext in this way. And the distinguisher is the following. We have 4 plaintexts as before, which are defined in this way. So we have a plaintext P1, which is just random. The second plaintext, so the first 2 variables of the second plaintext are different from the first 2 variables of the first plaintext, but the other 2 are equal. Then the third plaintext is basically the other way around. So the first 2 variables are equal to the first 2 variables of the third plaintext, but the other 2 are different. And then P4 is basically defined in this way. So the first 2 variables are equal to the first 2 variables of P2, and the other ones are equal to the second 2 variables of P3. Now, if we consider the corresponding ciphertext after 3 rounds, we have this property. So let's consider a byte position. If 2 ciphertexts are equal in this byte position, then the other 2 ciphertexts cannot be, and so it is not possible that the other 2 ciphertexts are not equal in the same byte position. So this cannot happen for 3 rounds of AES. So in other words, if 2 ciphertexts are equal in a particular byte position, also the other 2 ciphertexts must be equal in that particular byte position. It is not possible that in the same byte position, 2 ciphertexts are equal and the other 2 are not equal. But this event can happen in the case in which the ciphertexts are generated by a random permutation. So we can use this property to distinguish 3 rounds of AES from a random permutation. So just to give a quick idea why this property holds, if we have 4 plaintexts like this, then we know that after 2 rounds we have a zero sum, and this is due to mixed differential cryptanalysis. So what we can do is to try to set up a key recovery attack on 3 rounds of AES, which means we can just try to find the finite key by, for example, guessing the key byte per byte, which means we have equations of P4, and we know that there exists at least one key that satisfies this equation. If there is no key that satisfies this equation, then the ciphertexts are not generated by 3 rounds of AES. But now consider the case in which for a particular byte position, two ciphertexts are equal and the other two ciphertexts are different. So we know that this equation must have a solution, but if these two ciphertext bytes are equal, then the first sum is equal to 0, which means that this sum reduces to this one. And then this equation has a solution if and only if also these two ciphertext bytes are equal, which means that if we are in this situation, then the ciphertexts have been generated by a random permutation and not by free round of a yes. So using this property, it is possible to distinguish free round of a yes from random permutation, and you can find the details on the paper or on the video on YouTube. And that's all from my side. Thanks for your attention.
All right, thanks, Lorenzo. Very nice summary.
Thanks.
By the way, guys, I've actually posted the Zulip link in case you have any questions. Right now, I don't see any questions in Zulip. Do we have any questions from those who are here? Any questions for Lorenzo? Right, if not, Lorenzo, I was wondering, so it would not happen for the AES, but what's the probability for it to happen for the random case?
Approximately 0.3, so 30%.
Okay, it's quite high.
So yeah, so that's the reason why we just need few data.
Right. Okay. All right, thank you very much.
You're welcome, thanks.
So again, guys, if you have any questions, please feel free to put into the Zulip chat. Over to you, Maria. Next talk.
Okay, thanks. So the next talk is called Counting Active S Boxes is Not Enough. It's by Or Dunkelman, Abhishek Kumar, Eran Lamboy, and Soumitra Kumar Sanadya. And the talk is given by Eran.
Hi, thank you, Maria, for the introduction. I will be talking about our paper. Indeed, counting active S boxes is not enough. And basically what we do is we look at the Y-Trail design strategy and see how it can fill. So what we did in the paper, we discussed two constructions, of which one is secure, and both are secure when analyzing them using the Y-Trail design strategy. And for this talk, this short talk, I want to give one takeaway message. Be careful with the implicit assumptions when using the Y-Trail design strategy to analyze your cipher. We're not saying that you shouldn't use it or it's not valuable. It's a very valuable tool, but we should be all very considerate of things that can go wrong when using it to analyze. I will discuss this construction that goes wrong so we can see why we should be careful. So I will be discussing this construction. It's a 128-bit Feistel network. The round function consists of 4 SP layers, where the substitution layer is consists of the AES box, and the P layer is a 8x8 MDS matrix. And it uses 4 rounds, which we will see is not enough, but according to the Y-Trail design strategy, it should be enough. Now, the first thing we want to do, of course, is bound the maximum number of active, the minimum number of active S boxes in any characteristic through this cipher in differential cryptanalysis. And to do that, it's quite easy to do for this construction, because we know that any two consecutive SP layers will have 9 active S boxes due to the MDS P layer. So an active round will have 18 active S boxes, and since it's a 4-round Feistel network, we know that there are at least 2 differentially active rounds. So we'll have at least 36 active S boxes in any characteristic, any differential characteristics. Now, since we are working with AES boxes, we know that the maximum differential probability is 2 to the minus 6, which gives us maximum probability of 2 to the minus 216, which is plenty enough. Now, that is if we use the wide trail design strategy to analyze this cipher. But now if we look a bit more carefully, we see here a generic differential distinguisher for Renn-Festo network. If we start with 0 alpha as the input difference, then we get beta 0 as the output difference with probability P1 times P2. Now we want to know what P1 and P2 are, because if they're significantly higher, if the probabilities are significantly higher than 2 to the minus 64, then the distinguisher, we can use the distinguisher. Now we look at the round functions f2 and f3 as pseudo-random permutations, and of course we can compute the DDT for that. So let's have a look at that. In 93, O'Connor gave us the distribution of values in the DDT, which also gives us the probability of a certain differential transition. And what we see here is that with high probability, we have two transitions. So in the second round function, we have in the DDT and entry, alpha goes to beta with a high value. And in the third round function, we have beta goes to alpha with a high value. And these two events happen with high probability at the same time, of course. Otherwise, we can't use it. So now if we fill in the probabilities, we get this figure, and we see that the probability of this differential is 32 times 2 to the minus 64 squared, which is 2 to the minus 118, which is way larger than what we predicted using the wide trail design strategy. So what went wrong here? Clearly, there is a big gap, and that's all due to the differential that we're using. So in the wide trail design strategy, we're looking at characteristics, and here we look at a differential. So that's the large gap. Now, one thing we need to do is to check if just looking at the whole cipher as a 128-bit permutation doesn't give us a better distinguisher, or if this distinguisher is better than just looking at it as a 128-bit permutation. And for this, we can also use the work of O'Connor, and it says that the maximum entry in the DDT for a 128-bit permutation with high likelihood is 100, which gives us a probability for that differential of 2 to the minus 121. Now, this is a very extreme example, of course, but we see this in ciphers more often. So to conclude, be careful when solely relying on the wide trail design strategy for your analysis. It is a very powerful tool. It's very handy to use, but it also has some assumptions that can make your analysis invalid, or at least you need to take a bit more care while analyzing the cipher. Thank you for your attention, and here are the references. Well, there's one. Thank you.
Thanks a lot, Eran. What I was wondering while listening to your presentation is it easy to find this high probability differential that you identified here, or is it hard for an attacker to actually tell what the relevant differences are? Yes,
so in this case, it would be hard indeed to find. So you need to compute the DDT, of course. Or so you go through the code book. It's a full code book attack if you use this. In this case.
Because you would need the code book of the F function, I guess.
No, so each F is different because of the key schedule. because of the
Okay.
keys. So you will need the full code book of the cipher to find the. But there is a. So if you play the distinguishing game, there will be a high value somewhere in the DDT of, like, you will get a high value for some difference if you input 0 alpha for any alpha, not any alpha for a particular alpha beta. But it will be hard to find it as an attacker, yes.
Okay, so it has non-random behavior, but testing the non-random behavior is a hard problem.
Yes, I think so.
Okay. It's an interesting proof technique because there are already quite a few examples where we see that the prediction of the white trail design strategy doesn't really match what we observe, but usually the reason for this is quite different than what you explain here. So do you have some comments on how you went about finding this counterexample? So did you set out to find a counterexample, or did you just accidentally happen to find it?
Yes, we accidentally happened to find this. Yes. So, okay, yeah. We were working on something and then this came out. So, yes.
Okay, so a lucky find. Thanks a lot. Are there any more questions from the audience or from the other panelists? That doesn't seem to be the case. So thanks again, Eran, and let's head on to the next talk.
Right. I was wondering, quick one. So you mentioned that there's kind of a gap in the white trail design strategy. So based on the assumptions that underlie that, any advice how we should revise that white trail design strategy then to consider differentials?
So I don't think we should devise the white trail design strategy. It's a good tool to bound the maximum probability for a characteristic, but we should be aware that differentials can happen, and we are aware of it. There are multiple examples in literature that show that.
Yeah, I mean, if it's only limited to characteristics, then it's quite limiting in that case, because as you mentioned, it's quite common that people consider differentials.
Yes.
Okay, so we move on to the final talk. Shahram, would you like to share your screen? Yeah, so our final talk for this session is computing expected differential probability of truncated differentials and expected linear potential of multi-dimensional linear hulls in SPN block ciphers. It's joint work by Maria Eseda, Gregor Leander, and Shahram Rasulzadeh. And Shahram will be speaking.
Thank you, Rafael. I'm Shahram, and I'm going to shortly present our work. Differential cryptanalysis was introduced first by Biham and Shamir in 1990, and it is one of the most important analysis to analyze the security of block ciphers. And the main metric for differential distinguishers is the probability of distinguishers, that for a given input difference alpha and output difference beta for the given encryption with key k, the probability is defined as this equation. But attacker or we cannot usually use it because it is key dependent, and we need to have a expected differential probability that is average over all the key values. Finding differential over all of the block cipher is not an easy task, so usually attackers use the differential characteristics. That difference between the rounds is determined, and it is shown that probability of a differential is the sum of probability for all the characteristics that has the same input difference and the same output difference as the one for the differential. Computing these probabilities is not easy because you need to do these computations considering all the key values and all the plain text values. So even for smallest block cipher, it's not possible. But Massey and Morphy came with independent round key assumption that under this assumption, probability of a differential characteristic is the multiplication of probabilities for the differentials over one round. So you can easily compute the probability for differential characteristics considering this assumption. And in the case of S-box-based block ciphers, it is just multiplication of differential transitions probability over the active S-boxes. Even so, computing probability for the differential characteristics under this assumption is easy, but but for the differential, it is not still easy, and we need to consider all the intermediate state differences alpha 1 to alpha r-1, and this makes this computation very hard. Also, there is truncated differential, which is a generalization over having several input differences and several output differences in the differential distinguisher. And it is common that we use one activity pattern shown by delta and consider all the differential characteristics that their activity pattern is the same as the one giving with this activity pattern delta. There are three main methods to compute differential probabilities. The first one is enumerating characteristics and summing their probabilities together. And the second one is transition probability, that you compute probability of each round and put it in a matrix and then do the matrix multiplication. These two are simple, but either in time or in memory, they are very inefficient. And the third one is introduced by Murray et al., and it is very easy and very fast, but as we showed in the paper, the value given by this method can be untrustful. This method is based on the uniform differential probability assumption that any non-zero input difference for a S-box can go only to the non-zero values uniformly with the same probability. Using this assumption, the expected differential probability for a truncated characteristics is just a multiplication of linear transitions, multiplication of differential probabilities for linear layer. And this can be found like DDT computation easily. As you see, this multiplication is very easy, and it gives you the approximation for the probability of truncated characteristics. But we showed in our paper, this value can be very different than the exact value by the previous formulas. We came up by our own methods that the simplest one is assume that probability of a differential alpha 0 to alpha 1 conditioned by the activity pattern delta is given as this equation, and we first compute the most inner parentheses for each alpha 1 and save it in the table T1. And then in the second step, we use values in the table T1 to compute the second innermost parenthesis for each alpha 2, and again save it in a new table. We compute like this until the end, then we will come with the value of this probability for the differential. This is the most simplest one. That is the most simplest method we used. We developed and improved our methods to SPACs by SPACs, and then some other advanced methods for the block ciphers, which are using word-wise linear layer. We use our methods to find truncated characteristics for truncated characteristics, differentials, and linear halves for Midori and Iskini and Kraft block cipher, which these three are using quite similar round operations. In the first step, we found using the activity patterns with almost minimum active SPACs, we compute the truncated differentials, truncated characteristics probability, and we found 7-round truncated characteristic for Midori block cipher, which previously using Muriai et al.'s method, it says there is no such a distinguisher. And then we use the truncated characteristics with minimum condition in the linear layer, just which is the same approach as the Muriai et al.'s method. But we showed in this step, we showed that the given value can be very, very different than the one given by Muriai et al. Method, and also we use this these activity patterns to find differentials and linear halves, and we improved the previous found distinguishers for these block ciphers, especially for Iskini. We found 9-round differential that previously only 8-round differential was found. We also used our methods to compute the probability of truncated characteristics of Klein block cipher that was found by Leilmon and Neoplacencia previously. We showed that their estimation was close to the exact value, and also we found several new truncated characteristics and also differentials for Prince block cipher, which are comparable to the ones found by Ancanto et al. And even so, they were new for the previously found. We improved the probability for some of the differentials. Overall, we present several methods to compute the differentials probability and potentials for the linear halves. And there were several interesting results that the first one is the given value by Muriai et al.'s method is not that accurate. And the second one is that we saw that for the same number of rounds, having fewer active SPACs doesn't promise a better expected differential probability or expected linear probability, linear potential. So we suggest that for providing the security analysis for the new designs, we have to come with new strategies than just considering the number of active SPACs. That was all. Thank you.
All right, thanks, Sharam. So on your last point, new strategy, any specific new strategy in that case, instead of counting active SPACs? I
would say at least consider the differential effect. Like we show, our methods can be used for security analysis, but if you want to design and you want to comprehensively search for all the operations, it will take a time to use our method for general designs. And I would say just try to consider the differential effect or linear effect.
Okay.
Not only consider the number of activist boxes.
Okay. So thank you. We come to the end of our session. How long is our break?
Oh no, it's going to be a long break. The next live session is going to start at 6:30 p.m. India time. That is 1 p.m. UTC. So it's going to be a long lunch break.
A long break then. Okay.
Yeah,
So,
thank you, Rafael and Maria, for chairing this session. So in the meanwhile, viewers can on YouTube can view the recording of streaming of pre-recorded talks. So it has just started premiering on YouTube.
Okay, thank you.
Okay, thanks all, and see you at 6:30 p.m. India time.
Thanks, Rafael, Maria, and Srinivas. Yeah.